Today we are going to start with the notion of dictionary ordered relation. It's a special type of ordered relation. So let's start with the definition. Here we have two ordered sets and we are going to define an ordered relation on the Cartesian product of them. But actually before we do so, there is something about the notation that I must say, because we haven't really seen the section on Cartesian products in this book. It's nothing, it's just we use a different notation than the common one to write an ordered pair. Say you have two objects A and B. Their ordered pair where A is the first component and B is the second component is commonly written like this. However, the author, when discussing Cartesian products in this book, mentioned that this will cause confusion because the same symbol, the same notation also denotes an open interval in an ordered set. So to avoid that confusion, instead of this notation, an ordered pair will be denoted like this. This is not multiplication. Okay. From the context, it will be clear that when we write, say, 1 times 2, this is not the product of the real numbers 1 and 2. Rather, this will mean the ordered pair 1, 2. With this notational comment, let us now see the definition of dictionary ordered relation. Let A and B be two sets with ordered relations this and this respectively. We define the dictionary order relation. There is no special symbol for that. We are just simply writing less than on the Cartesian product of A and B as follows. For these two ordered pairs in A times B, we define we are going to discuss this diagram. Okay. Let me continue from here. So for these two ordered pairs in A times B, we define this to be less than this if either A1 is less than A2 and of course using the ordered relation that we have on A. That makes sense because you are going to use that to determine which one is less than which one. If this is the case, then we say that this is less than this in the new relation that we are defining. Or there is another condition. If that is also true, then also we will say this, and that condition is this. If A1 and A2 are same, but the second components are related like this. And because B1 and B2 will be coming from B, so we use the ordered relation on B to compare them. If either this is true or this conjunction is true, conjunction means and, conjunction of two simple statements means joining them by the word and. If this inequality is true, then we say that this is the case, or if this is true, then also we say that this ordered pair is less than this ordered pair. This is the dictionary order relation on the Cartesian product A and B of two ordered sets. The original sets must have ordered relations on them for this to be considered. Now, one of course has to check that the conditions for an ordered relation are true for this. That we will do in exercise 9. It can be shown that the above relation is really an ordered relation. On A times B. So when solving the exercises, we will prove this. Right now, let's assume that it is an ordered relation, and let's see some examples. Example 11. Consider the dictionary order relation on R times R, which we geometrically also identify with the plane. And what are the individual orders on these sets? That is your usual order less than, which of course, when do we say that A is less than B, where A and B are real numbers, namely when B minus A is a positive real number, that thing. So with that ordinary order relation on R and on this also, same thing, we consider the dictionary order on R times R. Now in this order, which points are less than which points? Because these are points, the elements in these are points for which we have a very nice geometric representation. These are points on the plane. Now what can we say about this order relation? Let's just see it geometrically itself. Instead of writing sentences, let's just draw a figure. So these are your usual Cartesian axes, rectangular axis. And this in fact is your R times R. See, there are some subtle things which we tend to almost forget. Truly speaking, R times R is not this plane. It's a set a set of some objects which are ordered pairs of real numbers. But this is a geometric representation of that set. Strictly speaking, these two are not the same thing, but according to the association we have set up between elements of this set and points on a plane, that we call this the plane. Okay, that's it. Alright, so let's just take, let's consider 2 points arbitrarily. Let's consider this point. Say this point is 1, we cannot write 1, 2 any longer. Okay. We won't write 1, 2, instead we are writing 1 times 2 according to our new notation. And say this point is 3 times 4, 3, 4. I don't exactly know how to say this, but you get the point. Now, which one of them is smaller and which one is larger according to the dictionary order? Note that the first coordinates 1 and 3 are not same, and 1 is actually less than 3 in the ordinary order we have on R. So, by the definition of dictionary order, this is less than 3 times 4. It seems as if this point lying at a higher, greater height than this one has some role to play here, but you obviously can see from the definition that's not the case. This thing entirely depends on 1 and 3. Because 1 is less than 3, on the plane, this point lies to the left of this point. And by the definition of dictionary order, that is why 1 times 2 is less than 3 times 4. Again, do not misinterpret this equation. It looks like 2 is less than 12. This is not multiplication. Keep that in mind. So, this is less than this. But actually, this is also less than some points which lie to its right but below. For example, you can consider this point here, which is say 3, minus 4, which lies on the same vertical line through 3, 4. If you consider these 2 points, then also 1 is less than 3. So, by the definition of dictionary order, this is also less than 3, minus 4, in spite of 2 being greater than minus 4. If the first components, the first coordinates of our points are not equal, then they will be, one of them will be less than the other, and that itself will determine which ordered pair will be less than which one. So, what do we see from this? From this we see that regardless of height, any point that lies to the right of this point will be greater than 1, 2. It's a left-right thing. Okay, fine. But, and similarly, any point, regardless of height, that lies to the left of 1, 2 will be less than 1, 2 in the dictionary order. Fine, so we have said in what relation the points of the plane are to 1, 2, I mean with respect to this order, dictionary order. But those points that lie either to the left of 1, 2 or to the right of 1, 2. What about the points that lie on this line itself? How are they related to 1, 2? This vertical line. Say we can consider this this point, which is say 1, 4. Which one is larger and which one is smaller? In this case, you have to use that other part of the dictionary order definition. because now the points to be compared are these, and 1 is equal to 1. So you then have to look for the relation in which 2 and 4 are. Since 2 is less than 4, in fact let me write the entire thing. Then you can see the definition and match with that. Note that 1 is equal to 1 and 2 is less than 4. So 1 times 2 is less than 1 times 4. Okay, so any point that lies to the right of your chosen point is greater than the chosen point, and any point that lies to its left is less than the chosen point. But points that lie on that same vertical line as the chosen point are greater or less like this. Any point that lies above this 1, 2 is greater than 1, 2 in the dictionary order, and any point that lies below is less than 1, 2. So dictionary order goes like this. I mean, if you simply think of the real line only, how does the order go from smaller elements to larger elements? Like this. I mean, this is the geometric representation of the real line, only the x-axis. So as you want to go to the higher and higher elements, I am not talking about size, okay, taking into account signs also, then it goes from left to right. In dictionary order, what happens is that first it goes like this and then like this. So this is the direction. It's not a single direction, but this is the sense in which the elements increase. They increase upwards along each vertical line, and when you have 2 points on different vertical lines, then the one that lies to the left of that other one is less. The one that lies to the right is more. That's the nature of dictionary order. And one more thing, why do we call it dictionary order? It is because this is the order that is used in deciding which words come where in a dictionary. For example, say you consider the word matrix and you consider the word nil radical, because in the alphabet M comes before N. So if we are thinking in that sense that as we go from A towards Z, we get larger and larger letters. If we define an order relation like that, then according to dictionary order, you have this. That's because, why I say dictionary order, because there are other letters also besides M and N. This of course does not involve 2 words with only 2 letters, because here we have only 2 components, but an extended version of that same idea. Because M comes before N, so the word nil radical will be found in your dictionary after the word matrix. However, say, actually I thought about a word. Do I have it here? Which matches with, oh yes. And next, what about the word matter, say? Think of these letters in these words as these coordinates, like these coordinates. M is equal to M, A is equal to A, T is equal to T, but then R is less than T, because R comes in the alphabet before T. That is why matrix is less than matter. It's like these 2 points. 1 and 1 are the same, but 4 comes after 2, 4 is greater than 2, so that is why 1 times 2 is less than 1 times 4. Here less than greater means which word comes before which word. So that is why this order relation is called dictionary order. That's the reason for this name. Okay, so having understood what this order is, let us now consider the next example. Example 12. Consider the state, this state, z plus or z plus times the half open interval closed 0 open 1 in the dictionary order. What are the orders on these individual sets? These are the usual orders that these sets get from the system of real numbers, the usual less than relation. Now what we are going to do, we are going to define a function f from this set into the set of non-negative real numbers by this rule, by this formula. Each input is going to look like what? It will be an ordered pair, where the first coordinate, first component is going to be a positive integer and the second component will be a real number between 0 and 1. It can be 0 but it cannot be 1. So in general it's going to look like this. N is a positive integer and t is a real number coming from this interval. And the definition is n plus t minus 1. What our aim now is to show that f is an order preserving bijection. And once we show that, these two sets will have the same order type. As ordered sets, they will be isomorphic to each other. You can also say like that. Okay, so let's now show this. First of all, you have to see that the function makes sense. That's the vague way of saying this. The technical word is that it is well defined. There are two things that you have to show if you want to know that a function is well defined. You take any input from the domain, the output according to the rule of the function should lie in that other set. That is the first thing. And the second thing is that for each input there should be only one output, uniqueness of output. Let us first see if our output really lies here or not. Let this, then n is greater than or equal to 1. Why? Because n is a positive integer, so the smallest positive integer is 1, so n is greater than or equal to 1. So n minus 1 is non-negative. Also, what is t? T is coming from this interval T is also non-negative. Hence, n plus t minus 1 is non-negative. Is a non-negative real number? So obviously it lies here because this is the set of all non-negative real numbers. And also it's clear that for a given n and t, this is a unique real number. See, if you really want to be absolutely rigorous about everything, you know what you want to do to prove uniqueness of output. You have to actually take two inputs, say n1 times t1 and n2 times t2, and consider them to be equal. n1 times t1 is equal to n2 times t2. From that, you have to prove that n1 plus t1 minus 1 is equal to n2 plus t2 minus 1. Now, equality of ordered pairs is defined in terms of equality of corresponding components. So, n1 will be equal to n2 and t1 will be equal to t2. So, obviously, n1 plus t1 minus 1 will be equal to n2 plus t2 minus 1. We are not going to write all these things because it's very easy. Also, we simply write n plus t minus 1 is unique. So, f is well defined. Usually this issue is pushed under the rug because you can see that it's really nothing much. I mean, it's something with which you have to start, but in most cases it is so simple that we do not even mention it. But that does not mean that you completely ignore it. You have to see for yourself that yes, this is well defined. Otherwise, if you just simply go on checking some properties, your relation may not be a function. But now we know that it's a legitimate function, it's well defined. Next we go for injectivity or one-to-oneness. Next, let n2 times t2 belongs to this such that the outputs are equal, and then we have to prove that the inputs are also equal. That will show that the function is one-to-one. n1 plus t1 minus 1 is equal to this thing, which is n2 plus t2 minus 1. Now, after cancelling minus 1 from both sides, we have n1 minus n2 equal to t2 minus t1. That's easy to see. And so, the absolute value of n1 minus n2 is equal to the absolute value of t2 minus t1. Now let us see what type of inequalities t1 and t2 satisfy, because both of them are coming from this half open interval. Since 0 is less than or equal to t1, which is less than 1, and 0 is less than or equal to t2, which is less than 1, So we want to know how minus t1 looks. Multiply here all the inequalities by minus 1. So that will give us minus 1 less than minus t1 less than or equal to 0, and let's write that one also. Hence, now we add these inequalities. That is why I did not simply flip the inequalities. I want to add these two sets of inequalities, so I wrote these ones like this. So 1 became minus 1 and came to this side. Now if we add, keeping in mind that we have strict inequalities here, so we will get strict inequalities again. 0 minus 1 is minus 1, less than. Although we have less than or equal to here, but here we have less than. So from properties of real numbers, this will be strict inequality. T2 minus T1, again less than. 0 plus 1, or the absolute value of T2 minus T1 is less than 1. Okay, so this is less than 1. Hence, n1 minus n2, because that's equal to n1 minus n2, minus t1 is less than 1. Alright, now t2 minus t1 may not, because they are real numbers satisfying these inequalities, so t2 minus t1 or even its absolute value may not be an integer if we simply use these inequalities. But n1 and n2 are both positive integers, so n1 minus n2 is an integer. It may be negative, it may be positive, 0, anything can happen, but it's an integer and its absolute value is a non-negative integer. So we now have a non-negative integer that is less than 1. So it can only be 0. And in fact, let us emphasize this fact. Since this is an integer, so this must be equal to 0. Hence, n1 must be equal to n2 and t2 must be equal to t1. That's it, just one more line. Thus, n1 times t1 is equal to n2 times t2. Assuming that the outputs are equal, we have successfully shown that the inputs are also equal. Hence, f is 1 to 1 or injective. Okay, next we come to the task of showing that f is surjective. For that, we have to choose any element in the codomain, the set of non-negative real numbers. Next, let y be any non-negative real number. Now this is where you have to use the greatest integer function or floor function. Then the floor value, or let me first write the inequality. Then y is non-negative, which simply means this inequality is true. Okay. Now, what can you say from this inequality about the greatest integer value of y? Y is some real number, y may not be an integer itself, may be an integer, but already 0 is an integer less than or equal to y, and we are talking about the greatest integer less than or equal to y. That cannot be less than 0, so that should be greater than or equal to 0. In some books, this notation is also used, but to indicate that this is the floor function, not the ceiling function, not the least integer greater than or equal to. So we just write like this. But we already know from the definition of this function that this is less than y. Greatest integer less than or equal to y. But the next integer has to then be greater than y, and the next integer is floor y plus 1. Okay. Now, I think it will be better if I do the calculation on this side. So what I am going to do, I will start with y, my chosen element or point, and I will write this as floor y plus 1 plus y minus floor y minus 1. Is everything balanced? 1 and minus 1 cancel out, floor y and minus floor y cancel out, and we are left with y. Yes. Now, do you see something where floor y plus 1 is a positive integer? Why? We already know that the output of the greatest integer function, any output, is an integer, but not this inequality. It is non-negative. So adding 1 to it will make it a positive integer. Even if it is equal to 0, adding 1 will give you 1, which is positive. So this is a positive integer. And now what can you say about these inequalities? I mean, what can you say about this using these inequalities? If you subtract floor y from y, then these last two inequalities give you this. This one is strict, i.e. y minus floor y belongs to this half open interval. So y is equal to, using the above thing, f of floor y plus 1 times y minus floor y. Again, this is an ordered pair. Okay. So we enclose the input within braces. So this shows that f is also onto. We have thus proved that f is a bijection, a well-defined bijection. But f needs to also preserve order. So that's the next thing. Next, let's use something else. A times b and c times db elements in our set, the domain of F, such that A times B is less than C times D in the dictionary order. You already know from the definition of dictionary order that this can happen in two ways. Either A is less than C, or A is equal to C and B is less than D. And we have to consider both the cases. Let A be less than C. Okay. Now, what is it that we want here? We want to show that A plus B minus 1 is less than C plus D minus 1, because this is the F image of A comma B and this is the F image of C comma D. That means we want to show that A plus B is less than C plus D. Okay. Now, and what does that mean? It means that B minus D has to be less than C minus A. Can we show this? You understand this, this is rough work. We are trying to see what we want to do. I mean, what we can do to get our thing. How can we get to this inequality? Do we know something about C minus A from this? We know that C minus A is a positive integer, which can also be written like this, greater than or equal to 1. We also know something else, because B is coming from here, D is also coming from there, but because B is coming from here, B is less than 1. And since D is also coming from here, D is greater than or equal to 0. D is non-negative. So, subtracting D from B will likely reduce it or keep it the same. If D is 0, then this is just B. If D is greater than 0, then this is less than B. In general, this is less than or equal to B. So that's how we have our thing. Okay, so now we can write this systematically. Then C minus A is positive, since C minus A is an integer, because A and C are integers. We have C minus A B minus D, or because we have written these things on that side, so A plus B will be less than C plus D, or A plus B minus 1 is less than C plus D minus 1, or F of A times B is less than F of C times D. Hence, F is order preserving. We have thus proved that this ordered set with the dictionary order and the set of all non-negative real numbers are of the same order type. Are of the same order type. As ordered sets, they are essentially the same. It's like having isomorphic groups in group theory or homeomorphic topological spaces. We will see these things, okay, when their time comes. Now, geometrically, this set is this. How? What is that diagram? You see, after all, both Z plus and this interval are subsets of R. So, this Cartesian product is going to be a subset of the plane if we are talking about the geometry. And in the plane, the set looks like this. This ellipsis indicates that these line segments continue to the right without any end. You can see why the set looks like this geometrically. For each positive integer, say n, your second coordinate of your ordered pair is going to come from here, and that will start with the first coordinate being 1. For that, we have this first vertical segment. All the points having the first coordinate 1 and the second coordinate lying in this half open interval will constitute this line segment, where this is the point 1, 1, which is not there in the set because this side is open. That is why we keep that side open. I mean, it's just a way of indicating that that endpoint is not there. It's not a point in our set. This point, however, is there. This is 1, 0. So it's that point 1, 0 on the plane. The other points lie here. For n equal to 2, you get this line segment. Every point on this line segment has first coordinate 2, and the second coordinate is something in this set depending on where the point is located. Like that it's going. But if we change the order of these two sets and consider this instead, then we get this. Geometrically, the set looks like this. Here, the line segments are stacked on top of each other and it just continues on upwards without any end. Although this set has the same order type as the set of non-negative real numbers, but this is another ordered set again in the dictionary order, but that has a different order type. But the other set in the dictionary order is of a different order type. Why? The question is why. Why are they different as ordered sets? You can see one thing, that in this set every element has an immediate successor. You can take any element. Say, let me arbitrarily choose this element. Geometrically, that is this point. What is the immediate successor of this point? What is the point that is just greater than this? It is that point which lies in the line segment above, vertically above this. Remember the definition of dictionary order. Any point that lies to the right. Remember that since the orders on these individual sets are just the order that we have in R, So we are still talking about the dictionary order that we considered in example 11. So any point that lies to the right of this point will be greater than this point, and any point that lies to its left will be less than this point in the dictionary order. But points that lie above this are also greater than this point, and points that lie below this are also less than this point. Luckily, the geometry, because the situation is like this, the geometry is such that there is a next point. Every time you consider any point here, no, there is a next point that is greater than this. There is an immediate successor. If you go back to what we defined in the previous video, you take any two elements A and B in an ordered set A. You can consider the open interval. This consists of all points in A that are greater than A and less than B. Did you see why we are denoting ordered pairs like using cross? Because otherwise we will confuse them with this one. If this open interval is empty, then we call B the immediate successor of A. There is nothing in between A and B. B is the next after A. That's the case here. If you consider this point and this point, then the open interval whose ends are this point is empty. There is nothing. That is why this is the immediate successor of this. Similarly, any point you consider anywhere, that will have an immediate successor. But that's not the case here. That's not the case here at all. You take any point, say here, say n times t. If that point is not the lowermost point in its segment, then, well, no, not exactly that. You consider points that are greater than this point in the dictionary order. Obviously, those points can only lie either in that same segment and above this point, or lie in another segment to the right side of this point. If you consider any point greater than this which lies in some other segment, then between this point and that point there are other points. So this is not going to be the immediate successor of this. And even if you consider some point in that same line segment, no matter how close you consider that point to this one, there will always be some point in between. So here no element has immediate successor. Here every element has immediate successor. As ordered sets, these two are different types of ordered sets. They are not order isomorphic. There are some other things that one can consider. For example, one can consider the least upper bound property that we have in the ordered set R in this general setup also. But that we will discuss in the next topology video. With that, in fact, this section ends, and after that we will start solving exercises. So that's just it for tonight. So see you in our next upload, whatever that is. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.